How do we begin? Yeah, so I'm here to talk about how they made video games back in the 90s, specifically 1993, mostly because that was 30 years ago. It's a nice big round number. So I thought I'd start off beginning, why do I know anything about this? So the main reason I started this project is actually I had an old video card that I pulled out of a box, and I was like, oh, I wonder how I can write drivers for this. And I tried doing it the Windows way, so it started with Windows 2000 and tried to work backwards to make a driver that way. And I found that was a little bit too difficult. So what I did instead was, well, what if we attack it, instead of from a modern operating system to lower level stuff, what if we started with the lowest operating system I'm willing to use, which is MS-DOS, and go up from there. So I embarked on that adventure. Primarily, my preferred programming language is Rust. I try and program everything in it. It is a fun challenge, and also I find its memory safety guarantees a nice sort of safety net, so that I'm not, creating programs that just die because I've programmed them wrong. So that was sort of how this started. So I found a library online that someone had started called Rust-DOS, Rust_DOS. And it has a couple of interrupts, basically some software that lets you call MS-DOS, like how you make file access calls and sort of these other pieces. And I started diving really deep into it. So I had decided I was going to implement all the DOS API calls and all these pieces. And so I embarked on this crazy journey to learn it all. I did not know how hard it would be. So that's sort of how it all began. Now, it's sort of interesting to think about 1993 and what was the landscape. So at that point, there were no 3D accelerator cards. Voodoo 1 didn't exist yet. ATI hadn't shipped their very first 3D accelerator, and they had not shipped the ATI hadn't shipped theirs, and NVIDIA hadn't shipped the NV1 yet. Those are all mid-90s, in 1995, 1996. So you had 2D accelerators, and you have to think about sort of what operating systems existed, right? So most popular for most users would be MS-DOS. OS2 had just started. And Windows 3.1, which was the first version of Windows that really sort of captured for a lot of people because of memory protection and using a lot of the 386. That didn't come along until July. So we'll just say, imagine it's February 1993 here. So the memory guarantees aren't there. 32-bit addressing wasn't there. It was an interesting time. There was more than 640K at least. There was that. There were VGA adapters, so VGA sort of started to gain prevalence in 1988 with the IBM PS2 series, and so you had some of those. The Visa standard hadn't quite sort of taken off yet, so it's really a lot of MS-DOS. You want to try and hit the widest number of users if you're going to bother sort of making these sorts of games and applications. So the interesting thing with that, so that's our landscape. So basically, we're in MS-DOS, right? 386, not a guarantee. Back in 1993, still very expensive computers, right? If you bought a computer, it'd be, $4,000. So a lot of people, bought into these things and sort of stuck with them for a while. So that's sort of where I started coming into this. So I was like, okay, well, MS-DOS, we found Rust-DOS. This seems to be working. And the interesting thing is, if you're dealing with the 286, protected mode existed, but protected mode didn't work the way people would expect. So people have no idea about any of this. Original IBM PC was based on an 8086 processor, and it was sort of an extension of a previous processor design, and they only ever expected that you would be able to access 640K. So what they did was the original IBM processors were designed to only run 64K. So they're like, how do we access more memory than that? And they implemented a very strange thing called segmented memory, where the pointers, like the way you normally address memory on a 32-bit standard protected mode operating system, is the memory is this big list of bytes, and they've just got addresses, and you'd be like, give me byte number 5, please. It'll give you byte number 5. Give me byte 7,732,000. It'll give you that. You just give it the number. Segmented memory is a little bit different. So in real mode doesn't have the nice addressing mode. It's all segmented. Real mode also gives you full access to the hardware. There is no protection whatsoever. And up until UEFI firmware, that was how computers booted. So 2010 is around when UEFI started getting popular. So it's really, it was the way for a good number of years. So that's the world. Now, interrupts are sort of an interesting situation for me. So I'm more familiar with interrupts from a microcontroller standpoint, so from system control. And in those contexts, interrupts exist so that when you're trying to do something with hardware, let's say a really common thing is you've got some data, you want to save it to your SSD. The way that works typically is you tell the hardware, like there's a whole bunch of stuff in the middle, but in essence, you ask the hardware, take this memory and store it to the SSD. And the old way of doing this before interrupts is you'd ask for it and you would just check over and over and over again, which is wasteful. That's not a good use of processing time. In the ideal world, you tell it to do something and it will interrupt you when it's done. And so that's what's called a hardware interrupt. And so it's a good way of being able to parallelize work without, basically parallelize work without having multiple cores, right? You say, tell me when you're done. And then other hardware is working in tandem with the main CPU. The interesting thing is, the way that MS-DOS was written, and CPM, which is sort of the precursor to DOS, on Intel hardware, they use something called software interrupts. And software interrupts are very much similar. So there's a table, and it says, if this event occurs, if this interrupt occurs, jump to this area of memory, execute this stuff, and then return from where you came from. Regardless of like what operating mode you're in, what you're doing, it jumps back and forth. So hardware interrupts, mostly so that you can do more than one thing at the same time. Software interrupts, mostly so regardless of what your program state is, you can jump to those things and it'll jump back for you. So the MS-DOS API is entirely interrupt-based. And I've been extending Rust-DOS, and so for some examples here, if I go to, I'll actually ignore the examples directory. If I go to the lib here, you can see that there are a fair number of them, right? So some early stuff is read character for standard input, read character for standard output, but there's quite a few. This table is not comprehensive. I've just been working through them because for me, it's fun to check boxes off. I want to like try and get everything implemented. But there are things, open file, close file. All of these pieces are done by calling into an interrupt and then getting results back. For people who don't know assembly language is sort of the lowest level language that most people are willing to write software in. It is a pretty shallow abstraction away from the CPU itself. So it's human readable, but these translate into numbers that the CPU on the computer knows how to execute. So as an example, if we say, what's a good one? Verify writes means nothing to most people. Open is a little bit too complicated. So if we take, let's just say, here we are. So let's say getting disk space. So this is an example of, okay, MS-DOS, you've got a hard drive. Maybe you've even got just a floppy drive. Maybe you've got 2 floppies. Give me the current drive parameters. And so this is an example of how you will ask the processor for this information. So first you say, this is the instruction I want to run. It's esoteric, 0x36, so 36 in hex. And then MS-DOS's interrupts, this is actually supposed to be 21. MS-DOS's interrupts are basically, they reserve integer or hex number 21, and depending on what the value in AH is, or for larger instructions, AH was a 64-bit register instead of an 8-bit register from way back, it will return information for you in different registers. And the way Rust does this is they've got this late out call, and it says, take the value that's in this register and store it into this variable. right? And then you do some calculations based on this stuff. Luckily, MS-DOS has been around a long time. It's well documented. There's information all over the internet. On a member, Marcel, gave me the book of PC interrupts. I have like every interrupt you'd ever want or ever need in that book. And it's written by two well-renowned people in the circles of really diving into PCs and the guts and trying to figure out sort of what things do, down to the point where like they've reverse engineered BIOS calls and know how to turn on and off CRTs in old luggable computers, some very old things. So, but that's largely interrupts, how it works. I thought they were mostly for hardware, but no, MS-DOS and other software work that way. So as an example, right, so we're sort of used to, video drivers or drivers for, gaming, where it's, you adapt it on this thing, install this thing. But the premise of drivers really is to try and take hardware, whether it's a mouse, a keyboard, or whatever, and sort of abstract the, thousands and thousands of different pieces and give you, as a programmer or as the operating system, a unified experience for how you're supposed to use these things. And MS-DOS, the way that worked is it wasn't necessarily a unified interface. Whoever got there first won. And so, for example, I have an Microsoft MS-DOS mouse driver called Mouse here. And it is basically the standard set by Microsoft for how do you get the position, how do you get the, how do you show the mouse cursor, how do you hide the mouse cursor, how do you set a custom pointer? And that's sort of where I played with it, because it seemed interesting to me at the time. And so, but what's interesting is like when Logitech came around, Logitech extended what the mouse could do. Logitech added a third mouse button on the PC. And so the Microsoft mouse didn't support it. So, but as Logitech came along, they were like, okay, well, this is what we have to do. This is the standard set by Microsoft. We're going to do this. And mouse drivers are a different interrupt number. They're interrupt number 33 hex. And so they have their own indexes for different functions that you're going to call, right? So to initialize the mouse, it's hex 0. To show the cursor, it's function 1. Hide the cursor, function 2. I wrote some helpers here just to simplify my code a little bit, and then there's sort of examples on how do you set the graphics cursor, right? Because there's a different cursor for text mode and graphics mode. So that's sort of how drivers work. So in real mode specifically, because the expectation was that you didn't access the hardware directly. As computers evolved and got into protected mode and 32-bit addressing and all of these things, that changed, right? It's actually more common for games made a little bit later to interface directly with hardware. So, for example, the Mach 64 video card that I pulled out of the whole reason for me embarking on this adventure, the Mach 64 video card has two different ways to address it. It's got one that uses sort of those drivers that run in MS-DOS and have real mode interrupts. And there's a whole other way where it's memory mapped I/O, which is how everything works now, right? The PC architecture eventually went over there, but that's how microcontrollers work. That's how most things work. That's how the phone in your pocket works. It's all memory mapped I/O. It's just much easier interface to use because you just read and write from memory instead of issuing these interrupts. So that's basically how that worked. And I adventured around with this. I have a few videos online, but I'll show you another video a little bit later. And then, so moving on to that, I was like, okay, well, we've got this situation. I've sort of figured out the mouse, and I'm just going through this step by step. What am I going to do with this? And my intent, unfortunately, I didn't have quite enough time to do this, but my intent was to make a little Breakout clone, because Breakout's pretty easy. We'll figure that out. So, I needed to figure out now video modes. How do you set different video modes? How does VISA work? VISA is a standard by a whole bunch of video card manufacturers that said, this is how we're going to talk to video cards. And again, that's eventually Microsoft came along with Windows and they built these drivers. And as long as you conform to those specifications for the drivers, regardless if you were NVIDIA or ATI or Matrox or any of those other people back then, as long as you conformed to Microsoft's interface and you provided the drive, if you wrote code that Windows could interact with in a unified way, it didn't matter. So this is all like it's fun archaeology, but it is not practical in any way unless you're dealing with like bespoke systems that cannot be replaced. Like this is all for fun. There's like, why do this? Mostly it's like my dopamine trip. I'm here to have fun. So into video modes though. So it's interesting because there were a lot of video cards that came out around early to mid 80s. So originally text mode, then Hercules for sort of high resolution text mode, CGA, EGA, all these things. I skipped over all of those. Like I came in, when I first got my first PC, I came in at a 46 with a VGA card. Like anything earlier than that, I just don't care. But there are weird situations with these older video modes. So what I'm accustomed to from Windows, so I've done some low-level Windows graphics work before, and what they do is there's things called device-independent bitmaps. And what that is just a block of memory that says, here's a representation of what follows, like basically so many bits per pixel there are, this is how big it is, width and height, and stuff like that. Please draw this to wherever I want to. And you can literally just take that memory out, do whatever you need with it, and then put it back in. So I'm very used to a big linear block of memory that just wraps around and you do what you need to do when you're done. That's not how these older video cards worked. They were very much, because this real mode segmented memory, and I should have dived a little bit deeper into this, but segmented memory, you can only access 64 kilobytes at a time, and what you do is there is what's called a segment register, and it lets you take that 64 kilobyte block, and it lets you slide it around in 16 byte increments. And so with a 16-bit segment register and a 16-bit sort of main register pointer, it really, you only can access up to a megabyte of memory. And so when you're dealing with just that limited amount, it doesn't make sense to get this big contiguous block of memory. A lot of video cards do it in a planar format. So where you write, if you want to make yellow, for example, you write a bit in a big block of memory, and then you switch the block you're writing to, you write another bit, and you switch to another block of memory, and you write the third bit, and then you get yellow. It's a lot of work. What I did, because I didn't feel like working in that difficult sort of situation, VGA does have one mode. It's mode 13H, and they're numbered from 0 to 13. And depending on the number, you get different resolutions. Both there's text resolutions and text modes, and there's also graphic resolutions and graphic modes. So highest resolution is 640 by 480 by 16 colors, and that's that weird segmented memory situation. The easiest mode to use is called mode 13H, and 13H is 320 by 200, and it's what's called a palletized memory, and that is actually a big bunch of bits. So you basically get bytes, so because it's 256 colors, 1 byte, 0 to 255, and it's just in order. And so I have an example of that here, and I can show you, this is a pre-recorded video. This is a bitmap viewer I wrote. And so the bitmap viewer cycles through different bitmaps, and so this was done in two parts. The first part was reading in the bitmap data, so reading the metadata, making sure that it's 320 by 200. In this case, it's actually 320 by 180. And then the weird one is setting the VGA RAM DAC. And the RAM DAC is given bits in memory, what waveform do you feed to the monitor to give it a color? Because typically, and you'll see it from the screenshot in the presentation or the preview of it, that's a whole different set of colors. So to be able to show this 0 to 255 that makes any sense, I actually take the memory or the color index table, and I actually rewrite the RAM DAC. So in this image viewer example, if I go to bitmap.rs, this is my bitmap reading. So there's a bitmap info header, bitmap color entry. This is the fun information that we need. And then there's just a load function that basically loads this into memory and then maps it over the area. So and then we can pull palettes and stuff like that. So that's just reading in the bitmap, and then in this code here, you'll see, so we load the bitmap in, and then we display the bitmap. So most of the magic is in viewer. And so you'll see here like VGA DAC color. And so the VGA, the RAM DAC is normally for RGB. If you're familiar with it, normally it's 8 bits, 8 bits, 8 bits. The RAM DAC is only 6 bits, so we have to actually do a memory shift. So I do, divided by 4. Two fun things about bitmaps, if you didn't know, they're written scanline inverted. So the top is written at the bottom of the file, and the bottom of the image is written just after the header. So that was fun to figure out. And then the other half is that the pixels are packed as not red, green, blue, but I think it's green, blue, red. It was a lot of fun. It was just completely inverted. So a lot of adventures there. So, but being able to set that as just a big block of memory, I take the bitmap blocks, flip it around, throw it into the frame buffer, like the video memory for the VGA card, switch the RAM DAC, and make that available. Next steps for this are going to be to blit. So blitting is the process that's just memory copies, but copying memory from one area of an image to another one, so I can do animations like a ball bouncing around for Breakout. But again, that's another project for another day. Again, I ran out of time there, but it's been fun. As far as sound, I actually have no idea. The Big Book of PC Interrupts, I have a little idea. The Big Book of PC Interrupts does have ad-lib interrupts defined and a little bit of Sound Blaster stuff, but I haven't dug into that yet. I really want to get a block bouncing first. So that's been my adventure specifically around these things. So hopefully that gives you an idea of like what was the hardware architecture, what was the software landscape, how the heck did you actually make use of the software that maybe some people have used in the past, and sort of how does video work. So hopefully that's been interesting. If there's any questions, unfortunately we don't have, when we show this later, there will be questions. I hope to be here, I won't be here. That's why we're recording it. But I'm hoping that if you've got questions, you can throw it my way, and I can get you answers. But yeah, any questions from the audience here right now?
Sure. So you've been working on this in an emulator?
Yeah. So there's been 2. So
is there a way you can demo with that?
Here's the problem: is I don't entirely know what state things are in, but we can try. Because the problem is I don't. So if I go to, we're gonna do it live. So other MSDOS. I don't even know what branch I'm in right now. Let's see. Breakout, we should be good. So if I do, so first I need to build it. So history, cargo. So what we want to do, it's a bit funny because the Rust's tooling was never meant to write MS-DOS programs. Yeah, so let's just try it. So image viewer.
There's a lot of command-line arguments to reset the compiler to work with that kind of memory environment.
Yeah, it just yanks a block of memory out of here, and it just rips out the header, and then it runs what's called a COM file. In MS-DOS, a COM file is literally, the program is just a block of bytes in memory, and DOS jumps to it. This is a CPM-ism. Actual exe files didn't come until later. So yeah, this is sort of an interesting situation. Right now, here, let's just do this. So git stash. So we're just going to stash everything. And this might compile now. We'll see. That's exactly what I meant. Oh, I nervous typoed that one. Yep, that seems to work. So if I do DOSBox, and what folder did I put it in? Yep. Let's see. So I used Rust. Yeah. So this is a much. There is text. Sorry. This is like a debugger. This is I rebuilt DOSBox with its debugger, so you get a little memory view and stuff like this. There's a much newer version of this though.
Your program acted as an image viewer, it displayed that image there.
It did.
And then went back to DOSBox.
And that you're using text mode to do this?
No, this is actually a graphics mode. This is 300 and.
Does it go back to text mode right after?
Well, I can go back to text mode.
Oh, there it is.
So 320, but you are the graphics mode.
Yeah. Yeah, and that's the only way I could get enough colors. So, because otherwise it's kind of meaningless. There is a version of this with more. Images, and I can't entirely remember where it is. Let's see. I don't remember if I merged it in. I don't think so. Well, maybe I did, because it's still here. So let's see if this main is a little bit nicer. Image viewer without an S. Yeah, so we don't have it. So example breakout. So unfortunately, I don't have anything particularly fancy. Yeah, so I need to dig it up. I'm a little bit disappointed that it's not there. There's other modes too, so if you wanted to. It turns out that I was having some interesting memory problems. So what I tried to do is use a different solution. So another one was to use I think it was QEMU. Oops. And this was just, I wanted to use real MS-DOS. So what you can do with QEMU, which is really nice, is it can emulate a full hard drive from a folder. So instead of having to inject things into an image, yeah, this is loading the wrong executable. This is I'm trying to implement a new memory allocator, which is totally foreign to me, using MS-DOS's memory allocation calls. That's why I needed the debugger. So I just need to recompile this to be in a different folder. And it should work. So tools. Yeah, so if I run this now, it should run in a similar way. So this is running DOS.
Oh, cool.
Yeah, this is running DOS 6.22. So it runs in actual DOS. The downside is actual DOS doesn't reset the resolution. But
Is there a call for that? I guess.
yeah, like I could write a program for it. I think mode is supposed to do it, but I don't know enough about mode. I used MS-DOS when I was 12. Probably from 12 until I was 14, and that's a long time
Does it
ago.
work in FreeDOS too?
Yes, actually. That's what I started with. Why did I stop using FreeDOS? I was curious of what I was hitting. If I recall correctly, I was hitting some really hard crashes. So I was just like, maybe it's FreeDOS. I don't know. But I'm pretty confident the way the default allocator works in this library just takes a big block of memory, whether it's allowed to get it or not. So like in MS-DOS, if I run, we've got a few more minutes. If I run mem here, it says like the total under 1 megabyte is 566K. I was pretty sure that my program was just writing over chunks of DOS that were critical for operation. So I've been playing around with it. I've just been learning stuff, but what I need to do is take a step back, actually build my breakout thing, and then be like, call it good. But it's been a fun adventure. But again, no practical application beyond like industrial control, because that's the only place where it's like I've spent enough capital that it's worth learning how this works. So yeah, that's adventures. We have time for like one more quick question. That took me a little longer than I'd anticipated. So cool. I guess we'll call it there then. Is it ready?
All right, well, on camera applause.